Today, we are tackling one of the fundamental building blocks of machine learning, logistic regression, combined with binary cross entropy laws, or BCE for short. If you have ever wondered how algorithms predict yes or no outcomes, like whether an email is spam or not, this video is for you. By the end of this video, you will understand the intuition, the math, and why BCE is the perfect loss function for this, and even how to code it in Python. First things first, what is logistic regression? It is a supervised learning algorithm used for binary classification problems. This means predicting one of two outcomes like pass or fail, win or lose, or cat or dog, or something like that. Unlike linear regression, which predicts continuous values like house prices, logistic regression predicts probabilities. It takes input futures like age or income and outputs a probability between 0 and 1 that the example belongs to the positive class. Now let's look at the magical backbone of logistic regression, the sigmoid function. As we know, in linear regression, we predict continuous values. To predict these continuous values, we use a linear combination of weights, the inputs, and a bias. So what a sigmoid function does is it takes this linear combination as an input and gives the probability as the output. So here, the z, which is the sigmoid function. So here, if you look at the formula of the function, we can write it as 1 by 1 plus e to the power of minus z, where z is the linear combination of weights and biases, which we use in models like linear regression. So in simpler terms, we feed the output which we get from linear regression into a sigmoid function. Now this gives us a probability of the input belonging to a respective class. So if the probability of sigma z is above 0.5, we generalize it and classify it as 1. Else we classify it as 0. But how do we train this model to get the right weights? Because even the sigmoid function takes a linear combination of weights and inputs and biases as an input. So how do we get the right weights to get the right classification outcome? That's where the loss function kicks in. And we use a binary cross entropy loss function here. This is the star for binary tasks. It is designed to penalize confident wrong predictions, partially while rewarding confident correct ones. So the formula for BCE is loss of y comma y cap. The y comma y cap is the inputs which we give to the function L here. Y is the real value of the output, and y hat is the predicted value by the sigmoid function of the output. This is equal to, so the L loss function is equal to minus of y into log of y cap plus 1 minus y into log of 1 minus y cap. Now let's unpack this. If y is equals to 1, the formula simplifies to minus log y hat. So if you predict y hat is equal to 0.9, loss is low, but about somewhere around 0.105. But if you predict y hat is equal to 0.1, loss spikes to about 2.3. For y is equals to 0, it becomes minus log of 1 minus y hat, mirroring the penalty. So why do we use log? Logs turn multiplicative probabilities into additives. This means if the probabilities are something like P of all correct is equals to P1 into P2 into P3 and so on, we can turn it into additives by using log P correct is equals to log of P1 plus log of P2 and log of P3 and so on. The sum of log probabilities is easier to work with mathematically, especially for gradient descent based optimization. The log emphasizes on small probabilities, making the loss explode when you're very wrong, but certain. Now, for example, if we have a true label as 1 and The predicted y hat is equals to 0.9. Then our BCE loss function, which is equal to minus y of log of y hat minus of minus y of log of 1 minus y hat. This will be equal to minus of log 0.9, which is approximately equal to 0.105. This is a very small loss. But if the actual label is 1 and the predicted y hat is 0.5, then minus of log of 0.5 is approximately equal to 0.693. This is a bit higher loss compared to the first loss we got. Now, if you look at the case where the real value is 1 and the predicted y hat is 0.1, then minus log of 0.1 is equal to 2.3. This is a very, very huge loss. So this is how the BC loss function penalizes the wrong values. For all the substitutions, we just took log of y hat because 1 minus 1 is 0. So this term will tend to 0. And minus y is minus 1. So minus log of y hat is what we're calculating. Now, to look at the average loss of model, we can uh, average this loss function like for all the data points I, from I is equals to 1 to n, where n is the number of data points we have. We can add we can add the losses from I is equals to 1 to n, and then we can average it by dividing it by n. And this will be the average loss of the model. Now, to get the perfect weights which fit in well into the linear combination of weights and inputs and biases, we use the gradient descent method. Now, the gradients for weights and bias will be the derivative of the loss function with respect to W for weights and the derivative of loss function with respect to bias for bias. And if we do the derivative of that function, we get the gradient as the error or y hat minus y into xi. This means that the gradient for weights is equal to the error between y hat and y and into the data point at which for which the calculation is taking place. And for bias, the gradient is just y hat minus y, which is the error. All know gradient descent uses these gradients to take and takes steps towards the perfect linear combinations which fit in well for the model, giving us a minimum loss. Now let's look into the code for logistic regression. This is the code for logistic regression, which we developed from scratch without using any external machine learning libraries. So first, we wrote a function to divide the input which we get into a test train split. So this function takes in the test ratio, the X list, which is the inputs, and the Y list, which is the output which we want, and the seed, which is the shuffling value, and returns an X train, Y train, X test, Y test data sets. And then we use a normalization function to normalize our futures for better predictions. Now, we use normalization because each future might have a different scaling value. And for the machine learning models to work perfectly, we need to make sure that all our futures are normalized and are on the same scale. Next, we define the sigmoid function. Now, this is the function which does the magic for logistic regression. This returns the probability by taking in the Z, which is the output from the combination, linear combination of the weights and biases. Uh, so the formula for sigmoid function is 1 by 1 plus exp of minus Z, as we discussed. So now we define the loss function. So here, the first term epsilon is a very, very, very small natural number. Why do we use this? We use this to avoid log zero terms in our function. So if y hat is less than epsilon, then we take epsilon as the output, which is a very small number. So it's very close to zero. So we'll use this instead of zero as y hat while calculating the loss. And then we return the value of the loss function, which is equal to minus of y into log of y hat plus 1 minus y into log of 1 minus y hat. Now we define a class logistic regression where we created an initial weights list for each feature and then an initial bias, and then we stored our learning rate into a class variable. Now we define a function called the predict prober. What this does is gives the output of the probability y hat from the input feature list. So z is equals to sum of w into xi for w comma xi in zip of self dot weights comma x. So for each feature, like for each data point, we have the weights for each column. Like for suppose if this is a matrix, and what this does is it takes each row and multiplies the value of each column in that row with the weights and sums them and adds a bias to it. And then it returns the sigmoid of this said linear combination. Now we define a predict function which sorts the probabilities. Like if the probability is greater than 0.5, then it returns 1, else it returns 0. Now we defined a fit function. Now what this function does is it finds the actual and perfect linear combination of weights this model needs. So first we iterate through the epochs or the number of steps this model takes in. Now we iterate through the input features dataset X and the output dataset Y with Xi, Yi denoting each data point. Now y hat is equals to self dot predict prober, the function, this function, which gives the output as a probability of Xi. And total loss will be equal to the loss will feed the yi, which is the real value of y, and y hat into the loss function. And we'll add this to the total loss variable. And the error, as we discussed for gradient descent using um, BCE in logistic regression, the value of gradient of weights is equal to error into xi, and the value of gradient of bias is equal to error. So error is equal to y hat minus yi, and the weights, the corrected weights will be equal to minus of the actual weights into self dot running, the learning rate or the steps which we take, and error and xi. And for bias, which for bias, the corrected bias will be self dot learning rate into error. Now the average loss will be total loss by the number of features which are there in X, or the number of data points which are there. And we return the loss, average loss for each epoch here. Now this is the test function which necessarily tests the model which we just trained. So it takes in it takes in the X test dataset and Y test dataset. It has a variable called correct, and for each Y and X in X test and Y test, we predict the value of Xi. What the split function does is it solves the values of the split prober of Xi into 1 and 0. And if now it checks, what it checks is if the Y predict is equal to predicted, like if the actual Y is equal to Y hat, then it adds one into correct. Resembling that for one data set, we predicted rightly, and it takes the accuracy and returns the accuracy. Now we already have a data set called logistic regression data set for this logistic regression model to test it. So we'll be using this data set, and we'll normalize it, and we will create or split it into the test range split, and then we'll fit it using a logistic regression class, and then test it. Now let's check how this works. Here we took a learning rate as 1. This is a very, very, very high learning rate. And our epochs as 1,000. So if you can see, our error or average total loss got stuck in between and stopped decreasing at a point somewhere around 260, from 260, because of the high running rate taking huge jumps towards minimization. Now, if we reduce this learning rate to 0.1, we can get a better approximation or a better model. Now let's check. So once we reduce the learning rate to a better learning rate, which takes in small steps and takes time to learn and go towards minimization, we got a better accuracy to a model. Some from 97. So the accuracy increased from 97 to 99 when we chose a better learning rate. So this is how logistic regression works. So this is how logistic regression works. Today, we learned how logistic regression predicts its outcomes and how binary cross entropy model is used as a loss function in logistic regression, and about the gradients which the binary cross entropy model gives for the weights and biases, and about the Python implementation of logistic regression from scratch. Thank you.